Hey there, and welcome. Today, we're going to pull back the curtain on computer programming. We're going to break down the fundamentals that power, well, pretty much our entire digital world. So let's just dive right in. I mean, really think about it for a second. You click a mouse, you tap a screen, and suddenly a video plays, a message zips across the globe, or a package shows up at your door. It feels like magic, doesn't it? But what's actually happening behind the scenes to make it all work? Well, the secret is actually kind of simple. Computers don't really think for themselves. Nope. Every single action they take, from the tiniest calculation to the most complex task, is just the result of them following a very, very specific list of instructions, one step after another. In that list of instructions, that's what we call a computer program. There are two words here that are absolutely crucial to remember: sequential, because the order of the steps matters a lot, and specific task, because every program is built to do one particular job and do it perfectly. So, that brings us to the big question. What is computer programming really? Well, it's way more than just typing weird-looking text into a black screen. It's really the art and the science of solving problems in a logical, creative way. And you see the results of it everywhere. Programming is how we get everything from our favorite apps and websites to the tools that analyze massive amounts of data. It even helps us automate boring, repetitive tasks. But here's the cool part. Learning to program actually rewires your brain a little bit. It makes you a better, more critical thinker. Okay, so if programming is about solving problems, where do you start? A lot of people think you just open up a computer and start hammering away at the keyboard, right? Nope. The best programmers, the really good ones, always start with a plan, a blueprint, before they write a single line of code. And that blueprint has a special name. It's called an algorithm. Now, don't let the fancy words scare you. The best way to think of an algorithm is just as a recipe. It's a simple, step-by-step guide written in plain English that explains exactly how to solve a problem from beginning to end. Before you can tell the computer what to do, you have to know what to do yourself. Let's look at a super simple example to make this real. Say we want to find the volume of a rectangle. What's our recipe? Well, step 1, get the length. Step 2, get the width. Step 3, get the height. Step 4, do the math using the formula. And finally, step 5, show the answer. See? It's a clear, logical plan that leaves nothing to chance. So we have our recipe, but how do programmers make that plan more concrete? How do they visualize the flow of logic before they get lost in the details of code? Well, they have a couple of really cool tools for that. You've basically got two main options in your toolbox here. On one hand, you have pseudocode. You can think of this as a more structured version of your recipe, kind of like a bridge between plain English and actual code. On the other hand, you have a flowchart, which is a totally visual map of your logic. It uses different shapes and arrows to show you exactly how the process flows, which can make things really easy to understand at a glance. And in a flowchart, every shape has a job. The oval tells you where the process starts and ends. A parallelogram is for any time you're getting input or showing output. A rectangle is your workhorse. It's for any processing or calculation. And the diamond, well, the diamond is super important. It represents a decision point where the program has to make a choice. Okay, so our plan is solid. We've got our algorithm mapped out. Now we face the big challenge. How do we actually communicate this brilliant plan to the computer? That is where programming languages come into play. They are the essential bridge between our human way of thinking and the computer's world of pure logic. And boy, have these languages evolved. We started way back with machine language, which is literally just ones and zeros, the native tongue of a computer processor. Then we got assembly language, which was a little better, but still really close to the metal. And today, we mostly use what are called high-level languages, which are designed to look and feel a lot more like human language. So what's the real difference? Well, think of it this way. A low-level language is like telling someone exactly how to move each muscle in their leg to take a single step. It's incredibly precise, but also incredibly tedious. A high-level language is more like just saying, hey, walk over there. It's abstracted away from all those tiny details, which makes it way easier and faster for us to build complex things. So, you might be wondering, is there one best language to learn? And the answer is a big fat no. There's no single best language, just the right tool for the job. The language you choose to build a fast-paced video game is totally different from the one you'd use to build a website or analyze data. It's all about the project's needs. All right, for the last piece of the puzzle, let's talk about the tools of the trade. What software do programmers actually use every day to write their code, check it for mistakes, and bring it to life? Let's look at the programmer's digital workshop. First up, you have to understand something called syntax. Now, don't worry, it's pretty straightforward. Just like English has grammar rules, every single programming language has syntax. It's just the set of rules about how you have to arrange words and symbols to make a valid command. Get one little comma or parentheses wrong, and the whole thing can break. So where do they write all this code? In a special piece of software called an Integrated Development Environment, or an IDE for short. You can think of an IDE as the ultimate programmer's workbench. It's a smart code editor that helps you write, checks your syntax for errors on the fly, and gives you all the tools you need to run and test your program, all in one convenient place. Finally, how does our nice human-readable code get turned into something the computer can actually execute? Well, there are two main ways this happens. The first is with a compiler, which takes your entire program, translates it all at once into machine code, and spits out a separate file that you can run. The other way is with an interpreter, which reads your code line by line, translating and running each instruction as it goes. So, let's just quickly recap the big ideas. At the end of the day, programming is all about solving problems. You start with a human-friendly plan, your algorithm or recipe. Then you use a programming language to translate that recipe for the computer. And finally, you use tools like IDEs and compilers to actually write the code and bring your solution to life. And that's it. From the initial idea to the final running code, that's the core of what programming is all about. So I'll leave you with a question to think about. Now that you know the basics of how it all works, what's a problem in your world that you think you could solve with a program?